nodes. So you allow peripheral nodes to communicate. In both cases, Q goes down. Okay, so you are moving away slightly in the sense that you're preserving the size of the network, but you are modifying the network structure slightly in a way that I perceive to be comprehensive, in a way that you're modifying the network in a comprehensive way, and Q drops. So, which is suggestive, I'm not proving 100%, that star is the only network, is the only topology that lives in the upper bound. Now, I do the same for the irregular networks. What I'm gonna do is you delete a single edge, okay? Delete a single edge. And what happens is you're gonna increase Q, which is also suggestive to, as you depart from a irregular network, you're gonna increase Q. You're gonna increase the variance of the posterior of the decision maker. Okay, so suggestive that you're pinning down the structures that live in those bounds. Fine. Now I'm going to extend the results to multiple connected components. So for the time being, I assume connectedness. Now I'm going to break connectivity and going to ask how does aggregation efficiency change with multiple components, right? So each one of the components, they're going to follow the same structure, but they're going to have, now the network is split into many components. Okay, now what this case is saying for the regular case. So imagine that you have a network, a undirected network with capital K components. Component 1, component 2, all the way to component capital K. And each one of the components, they have M subindex small k nodes. And if you add up all the nodes across components, you're gonna have N. Okay, in total, there are N, but they are split into irregular components. Now, what I'm claiming is if each component CK is D, K regular, then the orange Q is still 1 over N. So this is not a matter of connectivity, it's a matter of degree of homogeneity. Okay. I do the same here for the star case. I'm going to split into different components, in multiple components. Again, we're going to have capital K components. If you add up the nodes in which one of the components, you're going to restore small n. That's the size of the overall network. Now, the orange Q follows this term here, in which the red T is this T here. Okay, but just going to build the intuition here. I'm saying for large MQ, Q going to be approximately a Herfindahl index of the components. So for instance, if you have n equals 9, you prefer to have 3 stars of 3 than having a 1 star with 9. So the guy in the middle will mess up much more. So if you break down into small stars, yeah, it's still bad because those are stars, but at least you won't be, leveraging the mistake. At least you're gonna split into different center nodes. Okay, so but that's how it behaves here. There's a concentration. You don't like concentration. Okay, now the final part here. I'm gonna extend the analysis to random graph models, Poisson random graph model. Not sure the extent to each one of you are familiar with that, but let's say that you have n nodes and they're gonna meet with probability P, independent probability P. Okay. Then what happens here under the Poisson random graph model? So let's say that the average degree is this one here. Okay, is lambda over n. Then I have 3 regimes in which there is a sparse, so the average degree goes to 0. So it means you're going to a sparse network. The average degree diverges. So you are going to the complete network case. So everyone is bumping into everyone. And the one in the middle in which the average degree is fixed. Okay. Some number lambda. Then what I'm saying is that this orange Q goes to 0, kind of in a rate of 1 over n, 1 over n. What is the intuition here? Sparse network, it goes back to the original case. There's no network structure. First case, you are kind of killing the network. Third case, everyone is talking to everyone. It's a deregular, very heavy. This one here, okay, we know from this, from the transition phase, right? The phase transition property, that this Poisson random graph model will pretty much look like a deregular network, right? In which agent's gonna have this average degree here. So, but that's gonna differ in terms of the convergence rate. So here's more or less the numerical exercise. So here's the bound of 1 over n, so it's fine, it's respected, it's 1 over n. And here's the difference between the orange Q, the average across simulations, and 1 over n, which is the theoretical result. So you see that as the network increases, so we are moving from here to here, the curve is flattening out here, is being smashed, but it takes longer here for this part to converge, right? So there is some degree in the middle, which is 2, right? This number 4 here is the minimum degree to the power 2, so it takes longer to converge. Now, the last thing, I'm gonna extend to the preferential attachment model. Here is the case, is a dynamic construction of the network in which the probability that you're gonna connect to a node of degree D is proportional to the degree of the agent. So imagine that nodes are coming into the party and connecting with the high degree nodes with more probability. So then you have this degree distribution, right? So you have a power law here and producing hubs, star-like shapes in the network. Then this expected Q goes to 0 at this rate here, log of n over n, provided that the preferential attachment is not sufficiently strong to transform this network into a star. Just to show this more visually. So let's say that the probability of connection is proportional to the degree centrality of the agent I raised to some power alpha, which I'm representing alpha here, a number between 0 and 10, just picking some numbers, plus this scale free, this zero appeal performance, right? So if you have a degree 0, you still have a chance to get some connection. I'm fixing this a equals to 1, just giving like a little bit of a chance for 0 degree node to have some friends. And here I'm just varying the size of the networks. So, but the important thing is the following. If the preferential attachment is not super large, so yes, you have this monotonicity here. So Q goes to 0 as n increases. Then at some point, the preferential attachment model is so strong that it starts turning into the network into a star. Then you reverse the order. Okay, so you lose the monotonicity here. Okay, so and then you converge to the bound here, 1/4 again. Okay, so that's what happens. Okay, just to wrap up. So networks introduce no bias for the decision maker, but they're gonna affect the posterior variance. And this aggregation efficiency is gonna be driven by the degree distribution. Relevance, there are many real world applications in which experts, they talk to each other prior to inform the decision maker. And the contribution of this paper is introducing the social learning, linking network topology to aggregation efficiency. Now, research directions, at least for those who are kind of interested in this literature, to introduce some strategic information transmission, right? So you may have bias experts, ranking incentives. Why would I bother to share my forecasts if we are competing? Like the decision maker eventually is ranking us, and I care about that. So why would I bother to, to share my information? And the decision makers posterior updating with an observed but known to exist network, right? At least from a decision theoretical perspective, is, well, these people are informing what they think about this subject of interest, but I know they are kind of mixing up. How do I approach this in an optimal perspective? And the third one is repeated communication in the DeGroot case, which I already can see cases in which you may reach, in the spirit of Golub and Jackson, bias consensus, even with informed people, but with a different variance that is, is got by Golub and Jackson, and heterogeneous precisions. So I'm assuming agents are equally precise. The only layer of heterogeneity is the network structure itself. So I could have a second layer of heterogeneity is to say who is more accurate, right? Maybe the central node is more accurate, maybe the peripheral is more accurate, and so, okay? Thank you very much. I'm open for questions too. Thank you. I can talk offline too.